Hello, we are UMD Loop from the University of Maryland, College Park, and we are proud to present Athena, our rover for the 2025 University Rover Challenge. Our team, consisting of students from various academic disciplines including computer science, engineering, geology, and chemistry, has extensively prepared for this year's competition. Our design philosophy revolves around iterative improvement, with a strong focus on modularity. Backed by ample and rigorous testing, our team is confident that we will excel in this year's competition.
Our current propulsion systems are inspired by lessons learned from last year. Through exhaustive testing on last year's 6-wheel rocker bogie configuration, the rover wheel skipped while turning, and the suspension experienced bending from impact forces. This year, Athena features differential rocker suspension, custom polyurethane wheels, and 4 independent steering modules powered by 100-to-1 cycloidal gearboxes. This enhances agility and traction while reducing impact forces from steep drops.
Athena is equipped with a dual battery power system, featuring a large 24-volt 30-amp-hour battery to power mechanical systems, as well as a smaller 14.8-volt 4.2-amp-hour battery to power both communications equipment and the onboard computer. Both power systems can be independently disabled via remote commands, while maintaining the ability to shut off all power with an accessible emergency stop button.
Our custom PCBs, featuring STM32s, enable control of various sensors and actuators while minimizing cost. Every PCB on board Athena is controlled via CAN, allowing for a single, unified interface while maintaining modularity. Robust, long-distance communication is achieved through a 900 MHz radio, capable of switching subbands and enabling communication, even when line of sight is lost. A 3.5 GHz radio is also available with higher bandwidth for streaming video during line of sight missions.
Athena features a 5 degree of freedom robotic manipulator. Our 6061 T6 aluminum structure has been highly refined to minimize weight while guaranteeing no more than 2 millimeters of deflection. To move the structure, we are using custom 100-to-1 and 40-to-1 cycloidal gearboxes alongside 13-bit absolute encoders for precise control. Our shoulder and elbow joints utilize our 100-to-1 gearboxes along with powerful RMD X6-20 motors to ensure we can raise 6 kilograms from our max span of 1.1 meters. This year, we chose a lead screw gripper design for precise linear motion to pick up objects and move our custom linear actuator during the autonomous typing mission. The arm is also modular, taking just 2 connectors and 8 bolts to connect to the rover.
Athena's software architecture features ROS2 with our custom Cyclone middleware DDS. Our Jetson Orin Nano Super has been updated to the latest firmware and compiled with a real-time kernel to enable a 70% boost in computational performance over last year. Our ROS2 stack includes ROS2 control for both our omnidirectional swerve suspension system as well as for a 5 degree of freedom robotic arm. This allows for easy integration with Nav2 for autonomous navigation and MoveIt2 for autonomous typing, while taking advantage of our kernel's real-time capabilities. Our unified CAN bus wiring facilitates modularity between our physical subsystems, and our boot architecture ensures that all systems are immediately ready to go, even in the event of an emergency stop. From our base station, we can control and monitor all aspects of our rover, including up to 3 simultaneous high-definition camera streams. Furthermore, our control architecture allows for easy switching between control schemes, and system heartbeats allow for the automatic detection of an attached subsystem module.
The autonomous navigation subsystem uses the robot localization ROS package with an extended Kalman filter that fuses RTK GPS, IMU, and visual odometry data. We leverage Nav2 for path planning with elevation data-based global cost maps and Z2 stereo camera depth for local obstacle avoidance. The system employs a global A-star planner for path generation with a pure pursuit controller for precise trajectory following. Additionally, our custom YOLO V8 model detects the orange hammer and water bottle, while OpenCV handles the Aruco tag detection. This is all orchestrated through a behavior tree system that manages exploration, navigation, and object approach sequences.
The lowering platform houses both the regolith collection and life detection systems. The coaxial scoop modules collect regolith and transfer it through spillage-preventing internal geometry to a basin where a chemical buffer is added and mixed. The mixture is then moved into a reservoir for testing via peristaltic pumps. A series of tests determine both the presence of life-enabling resources and the quality of the environment from which the sample is taken. To collect the subsurface sample, the lowering platform deploys an auger and digs up to 14 centimeters below the surface. Temperature and humidity readings are taken using sensors on the tip of the auger. The cap extends while the auger simultaneously retracts, creating an opening for regolith from below 10 centimeters to enter the cavity. Finally, the auger retracts and the sample is transferred to an extended scoop module where it is sealed in a 5-gram cache and processed to detect life.
We're in it to win it. We've worked hard to get this far, and we've had fun along the way. See you in Utah.